All right, in this video, I want to take a look at how we use integrals to calculate center of mass, or center of gravity, or the centroid. These are all three different names for really the same concept. Um, Actually, in this video, I'm going to talk about it more along the lines of one-dimensional, even discrete case, and then in subsequent videos, we'll talk about it in two-dimensional um, and looking at it over continuous regions. So, just a little bit of physics here to get the idea of what's going on. I think it's center of mass, center of gravity. It really starts for me being able to understand a lever and a fulcrum, or for some of you, a lever and a fulcrum. I've got this straight piece of line segment, and it's not going to bend, and it's put on top of this fulcrum here. I'm going to place a weight on this side. Let's say right here I've got a 10-pound weight, and the distance away from the fulcrum is 2 feet. Right? And now I've got a 4-pound weight, and I want to know, where do I put it on here? So I'm going to place a 4-pound weight somewhere, and I want this to balance. I want this to not have this side go down, not have that side go down, that it's perfectly balanced. Okay? And what has to happen here is that what's called the moment on each side has to be equal. And moment is kind of a tendency to turn. And so what I see on this side is I've got 10 pounds times 2 feet. 10 pounds times 2 feet, which would be 20 foot-pounds of moment. Some people might say 20 foot-pounds of torque. It's foot-pounds. We've also seen foot-pounds meaning work, but I've got 20 of them on this side. And the thing is, in order for this to balance, I need the same amount on the other side. So that distance x there, this 10 times 2 has to be the same as 4 times x. Well, if 20 is equal to 4x, then divide by 4 here, x is equal to 5 feet. So you'll have balance when the moment on one side of the fulcrum is the same as the moment on the other side of the fulcrum. Now, what our job is going to be in this section is not to figure out how far to place things, but where the balance point is. We've already got things placed, and then it's like, where's the balance point? So let's take a look, for instance, at something like this. Let's say I've got 3 weights. Actually, I'm going to do this in mass this time. The point is, it doesn't really matter whether you're doing weight or mass. In fact, the names here, when I think what I just did on this one was more along the lines of a center of gravity in terms of weight, whereas what I'm about to do is more of a center of mass, because I'm going to do it in terms of mass. But the only difference between weight and mass is, force equals mass times acceleration. So the weight is just the mass times the acceleration of gravity. And so there's just a constant that comes in there, so it doesn't really affect the calculations at all. So let's put 3 weights on here. Let's again stick with our 10-pound. No, I'm doing mass this time. So I've got, let's say, 10 kilograms, and I've got another one over here of 4 kilograms, and I got another one out here of, let's say, how about 2 kilograms? Okay. And let's say the distance between these two right here is 7, and the distance between these two, so this is 7 meters, and this is 15 meters. Okay. What I want to know is where will this thing balance? Now, I haven't actually checked to see whether these are nice numbers at all. This is just, I make it up on the spur of the moment and say, here's some numbers. These are all in kilograms, all in meters, and let's see if we can find where the thing balances. Now, it turns out I'm going to do this essentially by throwing in any random coordinate system and using that coordinate system to then figure out where the center balances. So just to make this more work than I really need, let's not. Let's put a coordinate system right here. Let's say that this axis right here is like the x-axis, right? And let's put 0 right here. So this is 7, and this is 7 plus 15 is what, 22? Let's do that without the question mark. 22. Okay. So I'm going to calculate the total moment on this side. So the total moment is the sum of all the individual moments. That 10 kilogram thing is a distance of 0 away from my fulcrum. I'm thinking of the fulcrum right there at 0. So I got 10 times 0 plus 4 times 7 plus, what's this, 2 times 22. So I've got 4 times 7 is 28 plus 44. 28 plus 44 is 72. The total mass is 10 plus 4 plus 2, okay, which is, that's 16. So thinking in terms of the units here, the total moment was calculated as kilograms. Why is this? It's kilograms times meters, and this one was calculated, this is total mass, this was just adding up all the kilograms. If I take kilogram meters and divide it by kilograms, I'm going to just get meters. And this is what's called the center of mass here. The center is going to be the total moment divided by the total mass, which in this case is 72 divided by 16, and maybe I actually lucked out and got a nice answer here. 72 divided by 16 is 4.5. So my claim is that the balance point is right in here somewhere, right in here at 4.5. Okay, let's double check this and then see how we might view this in a little different light as well. So I'm going to double check this here by actually calculating the moment on each side of that. If I move the fulcrum over to here now at 4.5, then on the left side I've got 10 times 4.5. So 10 times 4.5 on one side, 4.5, there we go, which would be 45. And on the other side, let me see the other side. So from here to there, from 4.5 to 7 is 2.5. And then all the way out to there, 15 more than that, is 17.5. So I've got 4 kilograms at 2.5, and I've got 2 kilograms at 17.5. So let's write that down. 4 times 2.5 plus 17 times, 2 times 17.5. Okay. So if I calculate that out, this is 2.5 times 4, so that's 5, that's 10, plus 17.5 times 2 must be 35, and 10 plus 35 is 45. I actually have the same moment on the left side as I do on the right side, and I have found where the center is, where the balance point is. What we need to do in the next video is to do this similar thing over a two-dimensional region. Yes, we do, and I forgot to mention one thing. I was going to re-look at this problem in another way. I have 3 numbers here. I've got 0, 7, and 22. If I said take the average of 0, 7, and 22, you would say, okay, I'm going to add them up, 0 plus 7 plus 22, and divide by however many there are, 3. Okay, so the average is 29 divided by 3, which is 9 2/3. Okay, that's the way you take the average of numbers. But now if I said, wait a minute, no, I've got those three numbers, but I've actually, my list looks like this. I've got 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10 zeros, and I've got 4 sevens, and I've got 2 22s, right? And I said, take the average of those numbers, whoops, 2 22s, not 2 2s, 22 and 22. I said, take the average of all of those numbers. You'd have to say, well, okay, I'm going to add up all of these numbers. I'm going to all these zeros. So I have 10 times 0, and I've got 4 times 7, and I've got 2 times 22, and then I've got to divide by the total number that I have. Well, I've got 1, 2, 3, well, there's 10 of those, plus 4 of those, plus 2 of those. So I've got 16 numbers there. Well, if you take a look at this calculation here, 10 times 0 plus 4 times 7 plus 2 times 22 all divided by 16, I claim is precisely what we did here, the total moment divided by the total mass. The total moment was 10 times 0 plus 4 times 7 plus 2 times 22. The total mass was 4 plus 10 plus 2, 16, right? So this is the same calculation leading to an answer of 72 divided by 16, or 4.5. That this calculation here, I'm not just averaging 0, 7, and 22. It's what I would call a weighted average. I'm counting the 0 10 times. I'm counting the 7 4 times. I'm counting the 22 2 times. So each one of those numbers has a particular weight associated with it. And the average, the weighted average, is 4.5. This is literally finding the center of mass here, is literally finding the weighted average between 0, 7, and 2, where the weights are given by 10 kilograms, 4 kilograms, 2 kilograms. Okay. So the center of mass calculation is very much doing a weighted average.